of the material, whatever we're sticking in there. So for a parallel plate capacitor, we already knew what was the capacitance. It was some constant times the area of the plates divided by the distance between them. And now if you put a dielectric material in between those plates, you have to add this dielectric constant. What does your book use? Kappa? Yeah. You have to add that dielectric constant. That's a number greater than 1. Greater than or equal to 1. For a vacuum, it's 1. And air is almost 1 also. And then for other materials, it increases. All right, capacitance. So we have this way of dealing with capacitors. And they really, what they're doing, we kind of say they store charge. Really, they're storing energy. So the energy in a capacitor is 1/2 CV squared. It's Q squared over 2C. What else can you make it into? You can use the relationship, the Q equals CV, and change some of these things around a little bit. Oh, 1/2 QV. There we go. So the energy stored in a capacitor, 1/2 QV, and then using Q equals CV, you can turn that into one of these other two forms. And you want to pick sort of the one that, if you're given a problem and you know the capacitance and the voltage, you use 1/2 CV squared, right, to find the energy stored. Pick whatever you know in the problem. But these are all equivalent. Inside a conductor, right, inside a conductive shell. And even if it was not a conductor, it would still be 0. Even if that was an insulator. Because this is spherically symmetric, when you're inside, what you care about only is the charge inside of your location. Just like in being inside of a planet. Only the mass inside of your radius affects you gravitationally. All the mass on the outside cancels out because it's pulling on you in all different directions. So what do we end up with here? A equals B equals D equals E equals 0. And what is, we okay with that? But anytime you're inside a conductor, you know for certain 0. If there's no charge inside the conductor. If there was a charge inside the shell, then it wouldn't be 0. But as long as there's no charge inside. Okay. What's next? What do you do when you're outside of a spherically symmetric charge distribution? Treat it as a point charge, KQ over R squared. So which one is going to be biggest? F, because they're the same distance, but F has twice as much charge. We okay with that? Okay, turn it over. It says, find the electric field everywhere. Let's just do the first case. we're going to find the electric field everywhere. I'm going to plot it. Let's start with the easy one. Where is it? What is it inside the sphere? 0 for r less than capital R. E is 0, so I'll use what color? How about blue? Okay. And when we're outside the sphere, treat it like a point charge. So this will be KQ over capital R squared. And then it drops off as 1 over R squared from there, right? That's supposed to be a nice curve. So in this region, E is 0. In this region, KQ over R squared. Okay? Good with that? Now we want to do the electric potential at every point. I guess it should say on here. Let's take the potential is 0 at infinity. Maybe we should do the last part first. Let's do part 3 first. So at infinity, it's 0. As we come in from infinity, what is it? If we're outside of the sphere. Outside the sphere. That's correct. For inside the sphere, that's correct. It's she said because there's no electric field, it's going to be a constant. That's inside the sphere, right? There's no electric field inside the sphere. E equals 0. So V has to be constant. Delta V has to be 0. But V does not have to be 0. V has to be constant. But we're outside right now. And anytime you are outside of a spherically symmetric charge distribution, what do? Treat it like a point charge. What's the potential from a point charge? KQ over R. So it's just KQ over R. And when we get to the surface, it is equal to KQ over capital R. And it drops off as 1 over R as we move away. So something like that, right? It goes to 0 as we go to infinity. Oops. Something like that, right? And what is it inside? We said it's constant, not 0. V is not 0. V is constant. Delta V has to be 0. Because remember, delta V is the electric field times the distance, right? There's a minus sign somewhere in there. I guess I should have a delta S. Okay, so if E is 0, then delta V has to be 0. V has to be constant. It may be 0. It might be 0. 0 is a constant, but it doesn't have to be 0. What constant do we want it to be? Yes, whatever it is at the surface. Whatever V is at the surface, because we like continuity. So in this case, it's KQ over R at the surface. So I'm going to just continue that line so it's nice and constant and equal to what it is at the surface. And that's what my potential looks like. Now we can rank them. Let's just go ahead and put values in. The voltage at F. Where's mine? What's the voltage at F? K times the charge, which is 2Q, over the distance, which is 3R over 2, right? And what is that? That's 4/3 KQ over R. How about C? Half as much, which we should expect, right? How about E? What do we know that's going to be the same as? D, right? E and D are going to be the same. And it's going to equal V at the surface. So K, Q over r, which is at the surface. 2. And what's left? A and B. So the biggest ones are D and E. What's next? F. Then A and B. And then C. And they're all greater than 0, right? Did I get those right? I think I got them right. Okay, so go back over these, look them over. Make sure you understand them. Maybe go back and redo it for the second case, right, where the charge is twice as much. But anytime we are outside of a spherical charge distribution, treat it like a point charge at the origin. Anytime you're inside of a conductor that has no other charges in there, the electric field is 0. The electric field inside of a conductor is only due to the charges inside the conductor. You are shielded from anything on the conductor or outside of the conductor. Okay? Those need to just start coming like that. So if it's not coming like that, then work more problems. That'll help you, that'll help the speed. Just like practicing for a sport, you want to, in practice, it's awkward, it takes you more time. The more you do it, the smoother it gets, the faster it comes. So in a game, you don't have to think about it. It just comes naturally. That's the way you want it to be. You read that exam question, you just want it to come to you. Oh, I'm inside a conductor, E equals 0. That's the first thing that pops into your mind. Or I'm outside of a spherical charge distribution. I can just treat it like a point charge. Or I'm finding the work done and moving a charge around other charges. That's a very difficult thing to do. But, oh, wait, I know something. I know electric potential. That makes it much easier. I can use electric potential to find the work done. Okay?